Now we were solving optimization questions already. That's what we did yesterday. We had to come up with an equation that had only one variable on the other side so we could actually use our derivative. That's the concept. If you want to find a maximum or minimum, then your derivative would equal 0. So we need to find the derivative. Set it equal to 0 and then answer. But the hard part is probably setting up the equation because you have to take in all of that information. And this is just a little reminder that you did max-min problems first in grade 11 with parabolas. There's a little formula that you might have forgotten. Do you remember the axis of symmetry formula? Negative b over 2a, find the vertex. Okay, but this only works with quadratics, and calculus works with everything. But we'll start with a quadratic. So, ball is thrown vertically upwards at time t. Its height is given by this formula. And you see that this is a parabola that opens down. And because of that, it's going to have a maximum height. In grade 11, you would have needed to complete the square. But now that we have calculus, we just need to find the derivative and set it equal to 0. Not hard at all. And then, of course, once you found t, if you want to find the actual value, you could plug that back into the original equation because you're finding the actual point on the graph. So then your value gets plugged back into the original equation. Again, this can be a tricky thing. Your brain all of a sudden doesn't pay attention and you plug the 7.5 back into your derivative equation. Okay. Fred. Good old Fred wants to enclose a rectangular parking lot with 60 meters of fencing. Someone should have told Fred that he should have at least kept part of it open so cars could get in and out. Right? This is not going to be very... He's going to be stuck. I bet you he's working from the inside. He parked in the parking lot, built the fence, and now is in trouble. Okay. There's a building on one side, so no fence is needed there. Maybe you remember doing these ones in grade 11. So initially, you have two sides that you don't know. The building's on this other side. So imagine here, this green line, that's the building. We're looking at this from the top. Here's the parking lot that's completely enclosing Fred and his vehicle. It's rectangular, so these sides are the same. And that's why, in order to maximize the area, so again, we want to find a maximum area. If I take my highlighter, I need to have my equation area equals. Well, area is equal to length times width, which would be x times y. But since I know the total adds up to 60, I can get the y by itself. This lets me get my area equation with only one variable. It's not wrong if you had started off by writing area equals x times y. That's not bad, but we can't do the derivative of that because it has two variables. Well, we can't do the derivative nicely. Let's just clarify that. But now, we could find their derivative, set it equal to 0. And if x is 15, then y would be 30. And Fred has 450 meters squared to spend the rest of his life. Or maybe this is an auto body shop and there's a garage door here and they just don't want people to steal the cars overnight, so they enclose the, that could make sense. We can't necessarily, make too many negative assumptions about Fred. This question came from grade 12 pre-calculus. In grade 12 pre-calculus, you had questions like this. A rectangular sheet of cardboard measures 10 centimeters by 7 centimeters. And you cut out little squares so it can be folded up to make an open box. So here's the idea. I've got, there's a 10 here. I cut out those little squares, and then I can fold things up to see what they will look like. Your volume is going to be length times width times height. So if we draw, how good are you guys at drawing 3D pictures? Okay? So if I fold it up, the height will be x. So I'm going to draw just one side of the box and then go in 3D here. That's what the box would look like. We started off, this side was 7, but then you would subtract 2 x's away from that because they get cut out. And this side was 10, and you subtract 2 x's away from that because sides get cut out. And you multiply it all out, and you get your volume is 70x minus 34x squared plus 4x. Now, if you're allowed a calculator, I probably, and this was the exam, okay? When we have our calculator, we're strategic with our calculator. I would probably just stop at this moment right here, x, 10 minus 2x, and 7 minus 2x. Go to my calculator, go to y equals, and type that in exactly like this, x, 7 minus 2x, 10 minus 2x. Oh, I hit the wrong minus sign. You ever do that? There we go. And hit graph. Not happy with that graph right now, so I might play around with my window a little bit. Nope, not enough. And then I want to find that maximum. Okay? You might ask yourself, well, Mr. JR, that's not the absolute maximum. Why don't I pick a bigger value? Why don't I pick something further to the right? Because it gets bigger. Okay? Now, if we think about this question, though, there is some restrictions to our equation. I can't cut out more than 3.5. If I cut out x bigger than 3.5, you see that would completely, I'd have no cardboard basically left. Nothing left from this sheet to fold up. So even though my graphing calculator doesn't know I'm talking about a sheet of cardboard or anything like that, I have to be aware that there's some restrictions on this question. I can't go past 3.5 because then there'd be nothing left on this side and then I wouldn't be able to fold anything up. So if I do go to my calculator, I can go second, calculate, number 4, my maximum. It says start on the left. So what we want to do is we want to have this maximum in between the left and the right. Some shortcuts. It's already on the left. I can push enter. I don't know if you can see it. On my calculator, drew a little line. Now, some of you probably do this and go like, oh, I need to go to the right. So you start hitting the arrow button. Did you know that you could just type it? If you can be like, oh, 1, 2, 3. I know for sure 3 is to the right. I can see that. You can just hit the number 3 and it goes there right away. That can save you a little bit of time. And then it asks you to guess, push enter. So we know that the maximum is at 1.35 and the value is 42.4. So if this was a calculator question, that would be the fastest way to do it. And we want to be fast so that we're not wasting time on our exam wherever possible. However, if it was asking you to show the steps in optimization, you would take your derivative and make it equal to 0. Could you get the 1.35 without your calculator? Absolutely, but you would need the quadratic formula. Wouldn't be fun with those big numbers, but it would be possible. I'd probably divide by 2 to make it a little bit smaller numbers. But we already figured out that 1.35 from our calculator. You could also type this parabola into your calculator and find the x-intercepts. One of the x-intercepts is probably positive, the other x-intercept is negative, and you would have to be like, wait a minute, if I cut out a negative square out of the corner, is that possible? Something should tell you, right? These word problems, you always, make sure you always go back and think, is this realistic? And then you could plug in, here's the parabola, here's the two values, this one's bigger than the 3.5, that's why it's a problem. And then you could plug that value in, but we already found that value as well. This was the best way to do it. Draw that graph and find that maximum point.
What does it say for from? Like the arrow?
Okay, this is G for graphing display calculator. Good thing. All right, try the next one on your own. I'll put up the answer in a bit. right, here are the answers. So you can check if you got it right. This is kind of fun. I think it's kind of fun. We've got the square root graph, and you've got the 3.3 comma 0. And you're at 3, 0, and you say, I want to get to the square root graph, but I want to go there in the shortest way possible. Is this point the closest? Is this point close? Like, oh, it looks closer than one over here. How do I find that closest point? Optimization problem. So what do we know? We know that there are 2 points, 3 comma 0, and this point, which is x comma y, we could replace the y with the square root of x, because that's its equation. And then I have a distance formula, where I could do a squared plus b squared equals c squared. And my distance formula is x minus 3 squared plus the square root of x minus 0 all squared. And I want that distance to be a minimum. So we have to read from this question, nearest to the point, we want the distance between that to be a minimum, so we needed to make an equation that was distance equals. Do you remember your distance formula? No? Quick way to never forget your distance formula. All your distance formula is a squared plus b squared equals c squared. I don't think you forgot that. Okay? If I wanted to find a squared plus b squared equals c squared being the distance, so that's going to be the d, hence the square root, because what do you have to do with c squared if you want to get c by itself? You're going to have to find d. Now, if you draw a little right angled triangle here, does it make sense that this distance here, which is y, right, would be the square root of x minus 0, because there's nothing to subtract, but that distance goes from the square root of x down to 0. That's where this comes from. And the x value here, well, I would have to go 3, well, actually, it doesn't matter which way I do it. You can either do 3 minus x or x minus 3, whichever way you choose to do that. When you square it, it's going to be positive. Right? If you did 5 minus 4, you'd get 1. 1 squared is 1. If you did 4 minus 5, you would have gotten negative 1, but negative 1 squared is still 1. And that's so it's just a squared plus b squared equals c squared. That's all your distance formula is. If you simplify that distance formula out, it comes to the square root of x squared minus 5x plus 9. Okay? Now, we could take the derivative of this. Do you see it would be a chain rule? But one of the things about square roots if that inside is the smallest possible, then the square root will be the smallest possible. So if I just do the inside derivative to make my life a little bit simpler instead of doing it with the outside, I can solve for x being 5 over 2. I can see that that's going to be a minimum. And so the point on our graph that's the closest is at 2.5, comma the square root of 2.5. you like to play around with things mathematically, what I suggest you play around with is find the slope of this line and then find the value of the derivative or the tangent line slope at that line. I haven't done this, but my guess is that's the only place where the slope between the line and a point and the slope of the tangent is exactly 90 degrees. I bet you those two slopes are negative reciprocals. That's what mathematically my brain says. But it's something, if you want, you could play with it. This question came from an old IB exam. And in the old IB exams, they didn't just right away say, find when the surface area is the minimum, because they were afraid people would do the wrong steps in between and then they'd have to check all their work. So they would start by giving you the first step and give you the answer to the first step. And you just had to show that that was the answer. So here, we've got a cylinder with radius r and height of h, and they tell us the volume. They want us to show that the surface area would be this, because later, if you wanted to find the surface area to be a minimum, you need that equation with just one variable. So how do we get the surface area to look like this? Well, we know our volume. We know our surface area formulas. Each time you get a question that requires a formula, ask yourself if you have to look up the formula or if you've already got it memorized. And then we can substitute in. We have our equation only in terms of the variable r. And then I want you to try B on your own. Take a look if you're done or if you're stuck. We did a cylinder question the other day. We figured out the radius and the height. And it just so happened that the height was double the radius in that question as well. So it's kind of curious that the height is double the radius in this one. Does that always happen for maximizing a cylinder? Not maximizing, but minimizing the surface area to have the same amount of volume. Is it always double? I'm pretty sure 2 examples is not sufficient for a mathematical proof to say something always works. But it makes you curious. So then you just like randomly pick another number and solve another question exactly the same. And if it happens to work out to be double again, then you'd be like, All right, last question. How are you guys feeling? Do you want to try it on your own first? Okay. I'll put up the entire answer. Oh no, it isn't a perfect cube. I lied. Made everybody. The length is 36 and the y value is 18.